This video is going to cover tributary loading for one-way slabs. For one-way slabs, it is very specific that L2 over L1 is greater than 2, which means it's very, very, very rectangular. It's very long, skinny rectangles. So very importantly, L2 is the long direction, and L1s are the short directions. Now, obviously, you're thinking, well, the long direction is all three of the L1s. Well, yes, but we mean in terms of the small rectangles themselves. So, like, yes, this whole thing is a lot longer than L2, but L1 is each individual segment in here. So each one of these segments is an L1. So our L2 is our long distance to small distance for the one very particular rectangle that we have in here. So when we're looking at it that way, this is a one-way slab. So one-way slabs mean that when we break it up, we're going to distribute the load equally, half one way, half the other. So half is going to go up, the other half is going to go down. I like to think of tributary loading as fire escapes. If it's a very long, skinny hallway and both of the walls there have stairs to go down, well, you're going to pick the side that you're close to. You're not going to run down the hallway to find a different staircase. So you're just simply either going up because you're closer on that side or down because you're closer on the other side. So long, skinny rectangles, we're literally just going to go to the two long sides. So let's see this in an example. Here we have just a small one. We have just two rectangles here. We have 10 meters wide and 4 meters and 4 meters for a grand total of 8 from A to C and D to F. Not that that really matters. Remember, we have L2 and L1s. So we're assuming that AF and CD, the two end ones, don't actually rest on the member A, B, C, and D, E, F. We're assuming that those two corners kind of lay on the columns. That would be right under A, C, D, and F. So those guys are not going to play a part on the A, B, C, and D, E, F loading diagrams. Just to give us some weight, we've got a slab that's 270 millimeters thick, and it's made of stone concrete. So we're going to have to go back to our loading tables to figure out how much that actually weighs. And the point that we want to do is to draw all the loading diagrams for all of the members. So again, first up, we need to discover what type of slab this is. So L2, which is 10 meters, versus L1, which is 4 meters. That's equal to 2.5, which is greater than 2. So we are a one-way slab. Huzzah. So next up, what we need to do is we need to draw our loading diagram. We'll just draw it on top. So again, if half of this is going to go one way and the other half is going to go the other way, just going to draw a line down the middle of these, and half's going to go up for each of these lines, and the other half is going to go down for each of these lines. So half goes up, half goes down on each one. Very important to actually draw out the loading situation for the members. So next up, probably want to calculate what that load is that's being distributed in that way. So the slab, we said slab is 270 millimeters thick. It's stone concrete. So we need to go to table 1.3, and we would read off the table that we have 0.023. This is in kilonewtons per meter squared per millimeter of depth. Per millimeter of depth. And again, we do have 270 millimeters of depth. So our dead load that's being applied to this slab, which is just the self weight of the slab itself, is equal to that 270 millimeters times the 0.023 kilonewtons per meter squared per millimeter of depth. So our millimeters cancel out, and we're left with 6.21 kilonewtons per meter squared. So that's the dead load. That's going to be applied across this entire area. And our arrows are showing where it's being distributed. So let's go ahead and draw a beam out for our members. This is a very short beam, but even though this is AF and CD are going to be the exact same because they are the edge cases. So AF and CD are the same. And this is simply going to look exactly like the shape does up here in our loading diagram. So it is literally going to be this rectangle right here. That's what it looks like in our loading diagram up here at the top. That's what it's going to look like down there. So our loading diagram is just this uniformly distributed load. The question is, what is W? What is the value of that uniformly distributed load? So obviously it's part of the dead load, right? The dead load's playing a part, but the dead load is in kilonewtons per meter squared. And this is going to be across, again, if we're looking at the length of AF and CD, it's 10 meters. So we've got the width part taken care of. Right, we have the width part already drawn in our picture. So what I really need to know is I need to know this height right here. And the height of that member is going to be, remember if we're dividing half goes up, half goes down, then this distance is 2 meters for each of these halves, right? Half of 4 is 2 meters. So the closer 2 meters to AF is going to go to AF, and the closer 2 meters to BE will go to BE. So it's actually going to be dead load times 2 meters. So that W is going to equal 6.21 times 2. It's going to be about 12.4 kilonewtons per meter. So that's 2 of the members. We can draw the one for BE. So BE is going to look pretty much the same shape-wise, right? Shape-wise, he doesn't exactly look any different. We've just got uniformly distributed load. The difference for BE, though, is that BE has the bottom one going toward it and the top one also going toward it. So when we're drawing this, it's not an up or down. Just remember this is all kind of linearly in the same plane. So it looks the same here. The shape is the same, but the W is going to be different. The dead load is here, but again, we know that the overall width of BE is 10 meters, so we're not talking the 10 meter direction, we're talking this direction, and this direction is 2 plus 2. That's where that comes from. So our actual weight is our dead load times 2 plus 2, so dead load times 4. So it's twice as much as AF and CD. So that's going to be 24.8 kilonewtons per meter. Pretty massive. Now, we still need to draw it for, remember, ABC and DEF. But when we're doing that, we need to take into consideration that AF and CD do not act on A, B, C, and DEF. That does mean that BE does act on it. So the beam BE is laying straight down on top of AF, or A, B, C, and DEF. So we're going to need to find how much force is actually being applied at the ends here. How much is going to go on that member? How much does point E on this beam? How much does this point right here rest upon this this member. So we need to find the reactions here at the end. So the reaction is going to be, I mean, this is a very, very simple beam. You could sum the moments about B and you'll find the reaction at E, or because this is 100% symmetrical, it's literally only going to take half of that load, which obviously you'll see if you sum the moments. So this is going to be, we've got W, so it's 1/2 of that W times that distance of 10. So it's going to be 5 times W. So the reaction here is going to be 124 kilonewtons. Now if we go look at the beam, for A, B, C, and D, E, F, is there anything in our loading diagram, is there anything being angled towards those vertical members? And the answer is no. All of those forces that we have in our picture, none of them are going this way. None of them are going out that direction. They're all going vertically. So nothing's actually happening on A, B, C, and D, E, F, except for the joints at B and E. So actually the only thing we have going on in this diagram is we have the point load from B and E, and that point load is going to be equal to that reaction. So this is simply 124 kilonewtons, and that's all that's actually going on with member ABC and FED. Now, if you wanted to find how much goes to the columns, by all means, you could come back and find the reaction forces over here if we assumed that columns were only at A, C, D, and F.